configuration of an atom. So there are two ways. It's one way, but the other way was derived from that one. That you can figure out how to write the actual thing. So like to know if it's 1s2, 2s2, 2p6, and so on for one atom, for a specific element, pretty much. And that is using our periodic table. So there we go. And I'll separate. The best way to think of it is to think as each section of the periodic table as a block. So I'll color code it. This section right here, and helium, is red. I'm going to say this is blue. It's all of this, so like there's a line here. This section is green, and this is yellow, and this should be here too. So the red section means S as a subshell. The green section means D. The blue section means P, and the yellow section means F. So what does this tell you? What it tells you is where the last configuration will be. So let's say hydrogen, which is right here. So it's going to be in the S portion of the periodic table. So it will have to end with an S subshell. And what you'll do is, let's say hydrogen, it's 1, so it will be 1s1. And so I told you how to get this S. Now you know the last part of it. But you have to consider each of the parts of the periodic table as it goes down, the n will increase. So this first part will be n equals 1. This second one will be n equals 2. So as it goes down in a period, that's how it's called. It's a horizontal row. So the n will increase. So this is third, fourth, fifth, sixth, seventh. But for the case of the n on the D, so I'll write as green. It will be the row or the period minus 1. So row minus 1. So this will actually be, for this one, let's say SC, it will be 3D instead of 4, as you can see here, because you have to subtract 1. And for the case of the F subshell, it will be row minus 2. So LA will be 4, because it's 6 minus 2, 4. So now you know how to get the n. And finally, the way you get the number of electrons is you simply count. So I said hydrogen. Let's go with helium. Helium is right here. So let's say helium. It's 2. You can just write its atomic number. It says it there. And this will be here. Okay. And we'll start with, it's in the first row. So 1. It's in the red section. So it's S. And you just count 1, 2. 2 electrons. You just count the number of elements that there are until you get there, counting that element. So it's hydrogen and helium, so 2 electrons. Let's do carbon, the one I showed you in the previous video. So let me erase this part. And carbon says it's 6, so C6. And we'll start from. You always have to start from the beginning. That's the annoying part of writing electron configurations. That's why the abbreviations using noble gases is so popular. So we'll start 1s2. You fill it up before you continue. You always have to fill that subshell up before you continue. So we said that the maximum number of electrons S can have is 2, so that's that one filled up. Now we go to this part, so it'll be 2s2. It's still red, so it's filled up. Then we're in the blue section now. It goes from here to here to here. So we start with boron, and that is P, but it's still 2. That doesn't change for P. It's only for D and F that you subtract something. So let's write 2. It's the blue section, so it's P, and now you count until you find that element. So it's going to be 1 for boron and 1 for carbon. So that will be 2p2. And that's how you get the electron configuration of it, pretty much. So that's the first way people go at the electron configuration, and it's pretty much the only way you can do it. But there is an abbreviated form using this diagram. So when I learned it, they called it the waterfall because it looks like a waterfall in a way. But you can think of it as whatever you want, and you'll just follow the way the arrows point. So it'll go first 1s, as this arrow says, then it'll go 2s, then it'll go 2p to 3s, not to 3p. And the way I can explain you that is because it goes here. Sorry. Alright. Okay. It goes here from the 3s. Wait, what was it? Yeah. 2p to 3s. Yeah. 2. So it goes from this from this to this, sorry, because it will have to go like in a straight line every time. So the way this works is, let's say carbon again. You must be getting sick of carbon, but that's organic chemistry. So you just start from the beginning every time. It says that the first thing is 1s. So 1s. You fill it up. It says it's 2. What you want to do is you want to arrive to this number pretty much. And so we are at 2 now. Then we go to 2s. We fill it up. It says we have 4, still not 6. Then we go to 2p, and what we're remaining is 2. So now we have 6, and that's how you write it. So let's do something different. Let's do. Let me see. Aluminum, so 13. So I need more space. Yeah, this is why you use the noble gas abbreviation. So 13. It will be 1s2, 2s2, we got 4, 2p6, the maximum. Now we got 10, and then from 2p goes to 3s, 3s2. And finally 3p1. So we have 4, 10, 12, 13. So let's check our periodic table. Aluminum is right here. So yeah, it should be 3p1. This is the first electron of the p subshell, and it's on the 3rd row, so it makes sense. So if they allow you to use this on a test, or if you can just memorize it, it makes it a little bit easier if you don't understand the periodic table method better, but you can always prove it using the periodic table. And just so you can see it, I'll show you how the abbreviation works for aluminum, something a little bit longer than what we have done. So it's Al13, and we gotta check which is the first noble gas before aluminum. So it seems to be neon. It's in this right here, and so neon is 10. We're missing 3. So because it's a noble gas, after it there will be an S. In this case it's 3s2 or 3s. So it'll be 3s2 and then 3p1. So it's way shorter than writing this whole thing. And when you write transition metals, it becomes worse. And yeah, people like writing the abbreviation method better. And this is the case only for atoms. In the following video, I'll be talking about ions and transition metals. If you liked the video and you found it helpful, be sure to like it and share it with your friends.